So, hi, I'm Maria, and me and my team chose such topic for our semester project, which called word embedding via matrix factorization, and we chose next dataset, which holds 17 million tokens, and we took it from Wikipedia, and we limit our vocabulary by 10,000 words. So it would be easier for us to work with them. And next, what is our main goal? Is to embed words, which means to make them turn each word into some vector, an array of numbers. This similar meaning will be close to each other, like this. And words that are not really similar at all. For example, like coffee and maybe newborn will be really far from each other because they do not as often used in one sentence and as, for example, dog and love. I don't know, we love dogs. So how are we going to do that? At the beginning, let's define what is co-occurrence matrix, and we will work with it later. Let's call it M, and Mijth element of this matrix is how often word I stands within 5 words to word J. For example, let's take word I and word dog. If they stand within, like, I love my spectacular, beautiful, good dog, then it would be counted as one. And we built such matrix, and this is very sparse matrix, very big matrix, 10,000 by 10,000. And it is not convenient because every word has 10,000 10,000 number vector, and it is really big and it is really hard to work with that. So, and we encounter another problem, which is words like the, my, and so on, that encounters mostly at every noun, and we need them for the context and for embedding because they will make our embedding much worse. So we need to somehow work with them and not make them such intervene in our embedding. So we introduced PMI, pointwise mutual information, and I will write a formula and explain it. This is, I hope you see it well. This is joint probability, which stands for we add all numbers from co-occurrence matrix, and that would be total. And we divide it by Mijth element. So this number would be really, really small, and this number would be really, really big. And here at the denominator, we have marginal probabilities of Pi and Pj, and that is basically we adding the whole jth row and divided by total. And total, I explained it what it was. So when these two words will be independent, and by definition of independence, we know that this thing equals to this thing, so it would be equal to 1 if they are independent. What means independent? They are not sounding as a total nonsense in one sentence, but it is not as often as it should be for it not to count as a chance. So in order to make it more beautiful, we logarithmize it. So when the word is independent, then PMI would equal to 0. And if it is more than 0, then we will just know that these words stand together not just by a chance. And then we introduce PPMI, which is just positive pointwise mutual information, which would be maximum between 0 and PMI. of these two words. In order for our matrix to not have like negative values. Okay, what's next? We have a matrix which this problem is this my is solved, but the problem, this spirity of that matrix is not. So now we will use singular value decomposition, and full SVD has such formula: U multiplied by sigma, where sigma is diagonal matrix, where at each element sigma 1, sigma 2 is bigger than the other one, and this matrix multiplied by V transposed, where U and V transposed are orthogonal matrices, which means that their columns are orthonormal, which means that their columns has length of 1. This is full SVD, and for our so this thing would equal to M, our matrix M, which you've seen before, and now we don't need the full decomposition, but let's look at what we can rewrite this formula as, and that would be just sigma 1 multiplied by U1, V1 transposed, plus and so on, till the end, till there are no zeros. What is this thing? It's like a pattern. The strongest pattern, in our case, it would be something from Wikipedia, maybe some scientific terms and so on, and they will be in the first pattern, and this is the strongest pattern. For example, theory of probability, this is the strongest pattern here. And then we will have the second strongest pattern, for example, linear algebra, and so on and so forth. Okay, so each element from addition stands for this thing. Now we need to truncate it. Truncate SVD just to make it shorter, not 10,000 by 10,000. So we will make MK, which would be UK. So we cut off all the elements after kth element. So it's basically the same, but truncated, cut it. So why we use k equals to 300? Because by Eckhart-Young theorem, it is the best approximation, so we will not lose anything, but it's still approximation of MK and not the whole MK, which would be better, but we don't like to work with such big and sparse matrices, and we will approximate it, and it would be a really good approximation. Let's return to how we will embed words. We will construct embedding matrix, which would be UK multiplied by sigma k, and not just sigma k, but a squared sigma k, because the elements that stands at the beginning of the sigma k will be too large, and it would scale UK too much, and by UK and not VK, because we could take VK, but it's just simpler. You can take either of them. So we have 3 different variants how to do that, and we chose this because it reduces how sigma k impacts, and it just scales them. And as I said before, now we have embedded words, and we will have them as a vector, so we can represent them, for example, as that. And the difference between the 2 words, how they are constructed in the sentence, will be measured by cosines. So the smaller cosine, the words are more natural to work together. And that's it. I can show some example. For example, we have embedded word king minus man plus woman, and that would equal to queen. So we have vector king, and we delete the gender, the vector of the gender. It would have something like, for example, 1, and woman will have something like 2, and we delete 1 and add 2 to here, and the closest word to this changed of king would be queen by cosines, so we will have this queen.